Imagine something that always moves at the universe's ultimate speed, the speed of light, suddenly slowing down, taking on the qualities of solid matter. This phenomenon isn't science fiction anymore. It's called a supersolid, a newly discovered quantum state where photons behave both as waves of energy and structured matter simultaneously. In quantum mechanics, photons always travel at light speed, approximately 300,000 kilometers per second. But researchers have now engineered conditions to dramatically reduce their effective speed, making photons interact so strongly they behave as if they've formed a crystalline structure. This isn't just theoretical curiosity, it's a brand new state of matter, previously unseen. Photons flowing smoothly, yet maintaining an organized, solid-like arrangement. Quantum physics calls this rare, paradoxical state a supersolid. How exactly did scientists achieve this incredible feat? Why does this quantum state matter? Could controlling light this way revolutionize technologies, or even reshape our understanding of consciousness and reality itself? Join us as we explore this groundbreaking discovery and uncover how quantum science is reshaping the future right now. At the 5th of March of 2025, a groundbreaking study published in the prestigious journal Nature has confirmed what once seemed impossible. Scientists have successfully manipulated light itself into a supersolid state, an exotic phase of matter that simultaneously behaves as both a solid and a superfluid. This breakthrough research, titled Emerging Supersolidity in Photonic Crystal Polariton Condensates, was led by Italian physicists Antonio Gianfate from CNR Nanotech and Davide Negro from the University of Pavia. The study explains that by carefully controlling the interactions of light and matter within a semiconductor nanostructure, researchers were able to create polaritons, hybrid light-matter particles that displayed supersolid properties. According to the paper published in Nature, these polaritons were confined in a photonic crystal microstructure, which allowed them to form a self-organized structured state, a quantum phase where photons exhibited solid-like rigidity while maintaining superfluid-like flow. But what makes this so extraordinary? For decades, supersolids had only been observed in ultra-cold atomic gases, near absolute zero temperatures. Now, for the first time, this phenomenon has been demonstrated using light itself, defying conventional physics. Further reports from Science Alert, Live Science, and Economic Times confirm that this experiment involved using gallium arsenide semiconductor microstructures, where laser beams were carefully tuned to force photons into a highly interactive collective quantum state, a state that no single photon could achieve alone. This isn't just an isolated lab experiment. It's a breakthrough with real-world implications. Scientists believe that supersolid light could revolutionize quantum computing, photonic circuits, and even next-generation optical technologies. But could controlling light in this way unlock deeper mysteries, such as the nature of time itself? As we dive deeper, we'll explore whether this new state of matter could challenge what we know about quantum mechanics, relativity, and even time travel itself. Stay entangled with us, because the real revelations are just beginning. So how exactly did scientists freeze light and turn it into a supersolid? The process may sound complex, but let's break it down step by step so that anyone, regardless of their background, can understand how this quantum marvel was achieved. At its core, this experiment was about controlling the behavior of light by forcing photons to interact with each other in a structured way, something that doesn't naturally happen. The researchers used a semiconductor-based photonic crystal made of gallium arsenide, a material known for its exceptional ability to manipulate light at the quantum level. Step 1. Creating polaritons, the key to supersolid light. Light on its own doesn't interact like normal particles do, so to make this possible, scientists trapped photons inside a specially designed nanostructured photonic crystal, a microscopic engineered surface that allows light to behave in a controlled manner. When the photons entered this structured environment, they coupled with excitons, which are bound electron-hole pairs inside the semiconductor material. This merging of light, photons, and matter, excitons, created polaritons, a new type of quantum particle that behaves like both light and matter at the same time. Step 2. Engineering the supersolid state. Once these polaritons were created, the next challenge was to make them arrange themselves into a structured yet fluid-like pattern, the hallmark of a supersolid. To do this, the researchers carefully tuned the laser input power and frequency, precisely controlling how the polaritons interacted with each other. As more polaritons were formed, they started to self-organize into a pattern, similar to how atoms arrange themselves in a crystal structure in a normal solid. But here's where it gets interesting. Unlike regular solids where atoms stay locked in place, these polaritons still retained fluid-like movement, flowing without resistance while maintaining their rigid structure. This is what defines supersolidity, a paradoxical state where particles act like a solid but move like a superfluid, defying classical physics. Step 3. Observing the supersolid light. To confirm that this was indeed a true supersolid state, the researchers used high-resolution optical imaging and quantum simulations. They measured how the polaritons distributed themselves and checked if their behavior followed the mathematical predictions for a supersolid. The results were clear. Light had entered a new quantum state of matter, never observed before in photonic systems. Why this experiment is revolutionary? This wasn't just an isolated theoretical prediction. This was real experimental proof that photons, which were once thought to be purely energy-based particles, can mimic solid-like structures while flowing like a liquid. The ability to manipulate light this way could lead to next-generation quantum technologies, advanced optical computing, and even new ways to control the fundamental nature of light. But does this also hint at something deeper? Could controlling light in such an extreme state help us understand the very nature of time? In the next chapter, we'll explore how this quantum discovery could have profound implications beyond technology, potentially challenging our understanding of space, time, and the very limits of physics itself. Stay with us, because things are about to get even more fascinating. One of the most mind-bending aspects of this discovery is that light is behaving as both a solid and a fluid at the same time, a concept that challenges everything we know about classical physics. This state is known as a supersolid, a rare quantum phase of matter where particles are arranged in a fixed, structured pattern like a solid, yet they also flow without friction like a superfluid. But how is this even possible? Let's dive into the quantum mechanics behind this paradoxical behavior and understand why this breakthrough is rewriting our understanding of light itself. The supersolid and superfluid duality. How can light be both? In classical physics, solids and fluids are distinct states of matter. One is rigid and structured, while the other flows freely. However, in the quantum world, particles don't always obey classical rules. Instead, they exist in wave-like quantum states, allowing for strange behaviors that defy common logic. Here's how both properties are emerging simultaneously in this frozen light experiment. Solid-like behavior, the ordered structure of light. Normally, photons are individual energy packets that move freely through space. But in this experiment, scientists created polaritons, hybrid light matter particles that can interact with one another. These polaritons self-organized into a structured, repeating pattern, similar to how atoms form a crystal lattice in a solid. This means the photons, instead of moving chaotically, were locked into an organized structure, forming a quantum solid-like phase. Superfluid-like behavior, frictionless flow of light. But unlike a normal solid, these polaritons didn't just stay fixed in one place. This is happening due to Bose-Einstein condensation. The particles began behaving collectively as a single quantum state rather than as individual particles. This collective state allowed the polaritons to flow without resistance, like a superfluid, meaning they could move through the system without losing energy. This is why light in this system isn't just frozen into a structure, it's also flowing freely, displaying quantum coherence, a fundamental characteristic of superfluidity. So, what is the role of quantum mechanics in this breakthrough? To truly understand how light is exhibiting this dual behavior, we need to look at two fundamental principles of quantum mechanics that are driving this effect. Quantum superposition, existing in multiple states at once. In classical physics, an object can either be one thing or another, a solid or a fluid, but not both. But in quantum mechanics, particles can exist in superposition, meaning they can occupy multiple states simultaneously. In this case, the light-matter polaritons are in a state where they exhibit solid-like rigidity and fluid-like movement at the same time, a truly quantum phenomenon. Bose-Einstein condensation is the foundation of supersolidity. This experiment relies heavily on Bose-Einstein condensation, a state where multiple particles behave as a single quantum entity. Instead of individual photons moving independently, they all begin to act together as one large wave function, creating the conditions necessary for both solidity and superfluidity to coexist. This is why supersolidity doesn't happen in normal conditions. It only emerges when quantum effects dominate at extremely low energies. Why is this a groundbreaking discovery? The ability to control this quantum duality in light could lead to a revolution in quantum computing, optical circuits, and next-generation materials. Imagine creating ultra-stable quantum bits using supersolid light, making quantum computers even more powerful. Or designing frictionless optical systems where light can be manipulated with unprecedented precision. And could this even help us understand deeper mysteries of space-time itself? In the next chapter, we will explore something even more intriguing. Could this quantum breakthrough help us understand the nature of time itself? This discovery is not just about controlling light. It might be unlocking doors to deeper mysteries that science has only begun to explore. By forcing light into a supersolid state, scientists have done something extraordinary. They haven't just manipulated photons, they've challenged the very nature of reality itself. But what does this mean for the future of science? Could this be the key to understanding time? Could it reveal hidden dimensions? Could it be pointing toward a deeper layer of reality that we have yet to comprehend? For decades, light was thought to be untouchable, always moving, never static. Yet here we are, witnessing structured, organized light that flows like a fluid while maintaining a rigid form. This hints that quantum matter can exist in ways we never thought possible, raising new questions about other exotic states of matter that might be waiting to be discovered. One of the greatest mysteries in physics is the nature of time. We know that relativity tells us time is not absolute. It stretches and contracts depending on speed and gravity. But in the quantum world, time behaves strangely. Particles can exist in multiple states at once, and quantum entanglement suggests instantaneous connections across vast distances. Now, with this super-solid state of light, we have structured yet flowing quantum behavior, something that could lead to new ways of understanding time. Is time truly fundamental, or is it just an emergent illusion? Could this breakthrough help us explore time dilation, controlled quantum time effects, or even deeper symmetries hidden in the universe? While this doesn't mean time travel is possible yet, it brings us one step closer to unlocking the deeper mechanics of time itself. And what if this discovery points us towards something even greater, something beyond time? One of the biggest open questions in modern physics is whether we live in a multi-dimensional universe. String theory suggests additional dimensions beyond what we can directly observe. Quantum mechanics hints at parallel realities, where wave functions exist in multiple possible states before collapsing into one observed reality. And now, supersolid light proves that photons can exist in structured yet fluid states simultaneously, challenging our assumptions about fundamental particles. Could this be evidence that there are more layers to reality than we currently understand? Could light itself be the bridge that connects our observable world to hidden dimensions? Could the fabric of the universe be built upon deeper unseen symmetries that we are only beginning to glimpse? While we don't yet have all the answers, one thing is certain. This discovery has changed the way we understand the quantum world, and its implications could be far greater than we ever imagined. Scientists are only beginning to explore the applications of supersolid light. In the future, it could be used in quantum computing, next-generation optical technologies, and ultra-precise sensors. It could lead to new discoveries about quantum gravity, helping us bridge the gap between Einstein's relativity and quantum mechanics.